All right. So, oh, another thing is and I still have some tweaking of the course website for this class. The other day, if you click now on the lab, on the far left, there's something that says laboratory. If you click there, now you can see some videos. I posted a video of talking about this telescope and another telescope. I also posted a video of a tour of the Whitty Observatory out there. So yeah. So if you go out there, give me a like. It's on YouTube. Okay. So I don't know what kind of demo we got. So telescopes. Telescopes are awesome. And we are visited by a second telescope back there, right? And these telescopes have definitely some similarity to them. But what they do, when I go like this, I'm kind of talking about the lens, or in a minute I'm going to talk about it's a mirror, okay? But basically it gathers light, okay? And it gathers light. What that will do is it will make the object appear more bright, okay? And also we'll be able to kind of see more detail than we can with the naked eye. Like, for instance, Venus right now, oh my gosh, it's beautiful. Have you seen Venus? And like last night, as the Earth rotates, Venus kind of sets in the west, and it has kind of this orangey color to it. So pretty. But if you turn a telescope to it, hopefully you can kind of see a little bit more detail to Venus. I'm thinking it's a given. The other thing, and kind of the last, these are in order, is they let us see things that are far away. Okay, and you might be like, well, that should be first. Okay. So there's two types of telescopes. This is just I don't have a whole lot of slides, but I want to kind of talk you through some things about telescopes. Some telescopes use lenses. Okay, that's called a refractor. Refractors use lenses. We got two R's though. And if you look at yourself in the mirror, you see your reflection. So a reflecting telescope uses a mirror to gather that light. That's it. Okay. And I've got some pictures down there. Can you see the mirror here? This is a refractor. And do you see that thing that looks like a little belly button there in the middle? Okay, that's kind of where that's what we call a secondary mirror. That's where, can you see okay, Ty? That's where the light is coming and then going back. Okay, that's a secondary mirror. And then check, do you see this little person down here?
Oh my goodness.
I know. This white thing, that kind of, at the end is kind of like on her telescope. At the end is the lens that's gathering light, okay? And that's the business end. That's very important. But this long thing we call the optical tube, okay? It's an optical tube, so it's a very long optical tube. That's the Ch6 observatory, I think. And the whole bottom kind of goes up and down because it's so big, and just to kind of be where you need to be to look through the end of it. Telescopes. So I'm going to kind of talk you through those three things. I said you'll be able to see more detail. So in general, what's this? It's my lens or my mirror. Very good. My lens or my mirror, either one. In general, the bigger you get, okay, you actually improve on all three of those things. You can see more detail, things look brighter, and you can see things more far away, okay? But I will say that size isn't everything, because it's also quality. There's some things in life that, it's the quality of it, not just the size. So you get to see more detail. Now, I had a funny thing came to mind. A lot of times people will come to the observatory and we'll be looking at the moon through like one of our big telescopes, and they'll say, well, can we see the flag? And my point is here that there's not enough angular resolution to see that detail, to see the flag. So kind of you gauge angular resolution by what sort of detail can you see. And I showed you a video taken through this telescope of the moon, and it looks like you see a lot of detail, but not enough angular resolution to see the flag. Okay? In general, if you double the diameter, you double the details. So I'll go ahead and swing this bad boy around. This thing right here is I think this is right, it's a dew shield. So I'm going to pop this off, okay? It's just to kind of, well, have you ever been out and you hit that transition period outside, it's cooling down at nighttime and you get the dew, okay? Well, we don't want that on the lens. So this gives it actually a little kind of cushion of air that less likely to get dew. So there we go, yeah. This is 4 inches, okay? So if I were to double that to 8 inches, okay, that would be a crazy heavy telescope. My optical tube would be longer. At the observatory, we have this type of telescope that is 12 inches. That's not 12 inches, 12 inches, about like that, right? 12 inches. Okay. So the biggest the longest optical tube out there, anyway, at the observatory, this is 12 inches. What do you think? Is this a lens or a mirror? How many people think it's a lens? Me too. That's a lens. These are similar. These are very. How do you tell? Well, one thing, it's at this end, and you probably can't tell. Okay, but it's at this end. If it were a mirror, and I'm going to try to convince you of this, actually it would be at this end. I don't know. But yeah, it's a lens. That's a good question. How can you tell? But I don't know, if you look, I don't know if you guys can see it, but if I look through here, I can actually see light down at the end. Can you guys see light down at the end? Okay. What you're doing is looking through clear down to where the eyepiece is. Okay. So angular resolution, that's kind of how that works. Detail. So I'm going to kind of talk you through how these work. Okay. I mentioned gathering light, and I kind of go like this, gathering light. I'm going to talk about actually where it gathers light to is what we call a focal point. Okay. But these sort of telescopes use refraction. The phenomenon of refraction happens all the time. Refraction is why diamonds sparkle. The reason diamonds sparkle basically is light goes through air, okay, and then light goes through your diamond and it changes speeds. As it changes speeds, it gets bent. And it has all these kind of cool things as it comes out. So refraction is bending. Happens all the time. Refraction, if you've ever, if you've been swimming, it's been so long since I've been swimming, with little kids and all that, but if you've been swimming and you ever kind of look down, do you ever look kind of disjointed? Yeah, that's refraction. Light's being bent because the light comes from the water, up through the water to the air, and it bends, and it appears at a different location. That's refraction.
I remember elementary school, how they show it to us as a glass of water, with a straw.
Yeah.
Like a straw or a pencil.
Yep, a glass of water, and it looks like it's kind of broken. Yeah, exactly. Refraction. Well, if I were to take this and take it apart, there's little screws there, but I don't want to do that. But I would see kind of a fat end here and a fat end here, okay, just like this. We call that double convex. Concave is kind of sunken in, convex is fat. So it's double convex. And so we basically, it's kind of like, remember Newton used that prism just right to make the light separated? Actually, that's refraction also. So anyway, it's ground just right so that light comes through, it's bent, and then it's bent again as it leaves the lens on the other side. And it goes back to a focal point. It's concentrated at a focal point. Sometimes I like to picture my focal point. I'm like, oh my gosh, all that little energy, all the little photons, all the little light energy is all to that little spot. Have you ever killed ants with a magnifying glass? Come on. Yeah. Or tried to start a fire with magnifying glass? Okay. What you've done is held it above the ground and tried to find right where the light would concentrate. So that's kind of what a telescope does. Awesome. Okay. All right. So this is that little person standing down there. Now when it says a 1, of course M is meter. I have a yardstick in here. Where's my axis of rotation? So this is a meter stick. So maybe it doesn't look like much, but at the end of that optical tube, this is what that glass lens looks like. I know. Now, the problem with glass is it gets droopy, it kind of drags, it kind of gets deformed over time. So I'm thinking that there actually, logistics-wise, there is a maximum diameter. I don't think you can get much bigger than this for this sort of telescope. But you can kind of see, this would be the focal point I was talking about, okay? And then to kind of, what I say, unpack that information, you put what we call an eyepiece right here. Okay? So here, my eyepieces, by the way this works is this is just a counterbalance right here. to kind of make it so it doesn't fall over from the tripod. So my eyepieces are right here. How do I do this? Now, a lot of times what we'll do with an eyepiece is put a little 90-degree thing in it. This is actually just a mirror. This isn't doing anything with gathering light or anything. This is just taking the image coming from the telescope and making it so I don't have to squat down and look at it. Okay, like that. It's just a right angle thing. My eyepieces are actually, they're bigger than I'm kind of used to. These are 2 inches. I guess I've had this telescope for a few years now, but this is a 2-inch diameter. And a lot of times your eyepieces will have different diameters. Another common diameter, that might be an 8.6 or 0.89. Another real common diameter is hobby, right? You're like, are you serious? My husband supports me in all this, so I'm looking for my, oh wait, I already put it in my eyepiece holder. There it is. This was it. This actually, this is 1 1/4 inches. So this is another really common. So 2 and 1 1/4 inches. And then the eyepieces, they always have like a number. So this says 13.8 millimeters. And that is actually, I should get this right. That is actually, say, this distance right here. Okay? And it's backwards. So 13.8 will actually give me more magnification. And the lower the number, then I have less magnification, but I have more field of view. More concentrated, smaller number, okay, a bigger number, bigger field of view. So a lot of times when we have a viewing session, I'll swap out eyepieces depending on what I'm kind of after, or what we're after. All right. There's that. Get you balanced again. Actually, without the hood on it, it's probably kind of out of balance. Okay, what else we got? So this is a refractor. So one of the things I just kind of want you to know is refractors use lenses, and we've got 2 refractors in here. They both use a lens, and how do you know? Well, you can actually kind of see through it to the eyepiece, and it's at the end, refractors. Reflectors, reflecting telescopes, and actually SCC has a couple of great reflecting telescopes. I usually go like this for my reflecting telescope, because what I'm doing is kind of going, I'm kind of giving that, now it's not a convex, it's concave. It's better than concave. To be best, actually, it's parabolic, if you're kind of familiar with shapes. Okay? So what that does, what the mirror does, and usually it's at the butt of the telescope, is it gathers light, and like what a mirror does, it reflects it back, and because of that shape, it reflects it back to a focal point. Okay, that's a reflecting telescope. And I think I'll probably bring one in. I just had my hands full setting this one up. We've got another one in the lab. We can do that.
So like it comes in, bounces off.
Bounces back at an angle to a point. Yeah. Now, how do we get to this information? That awesome information. There's actually 4 different ways we get to that.
Yes, I was wondering
Yes,
how you get to
4 different ways, and they're listed here. Remember a little bit ago, I told you the belly button for the reflecting telescope, that belly button. That was what we call the secondary mirror. And this is up here. Do you guys have this slide? No? Oh, okay. I must have inserted it afterwards. Okay. So just kind of, there'll be nothing on the test. What I really want you to know is a refracting and reflecting telescope. But with these reflecting telescopes, they all have, you're going to see this kind of, it doesn't look like a concave, but yeah, concave mirror back here, but it's coming back to a focal point, and near that focal point, the image that's still converging is shot out the side. That design is called a Newtonian focus. Okay, so it's shot out the side. I've got one of those too. It's, yeah, it's a good one. Now this other one, your mirror, your primary mirror down here next to the letter C, it's got a hole in it, a honking hole in your primary mirror. But that's okay. It's still gathering light. taking it back to the focal point, we have a secondary mirror, but instead of going out to the side, it goes right back down the tube. This letter C is called a Cassegrain focus, and that's the other telescope I think I'll be bringing in sometime to show you. So our eyepiece is going to be shot out the butt. There's the mirror, okay, light comes down the mirror, there's a secondary mirror up here, and then it comes back down the butt. Okay, it's a kind of common design. Then these other two are kind of less common, I think, kind of catch-all. The Coude focus. This last one, so where would you have to go to get the image for that last one? You just have to be kind of floating in the optical tube. Yeah. So actually there are, fancy telescopes. If you just put a detector there, okay, that might be all you need. You're not going to be able to walk up to it, okay. But that's, to me, that's called a prime focus. B is prime focus. I don't know if this is right, but it's almost like you don't set somebody there, but you have somebody monitoring that point. That's all the information being concentrated there. That's where your ants are dying. Okay? Anyway, two types of telescopes. Okay, so this one, is it a refractor or reflector? What do you think? Reflector, exactly. Do you see the little secondary mirror? Yep. So, this is a Cassegrain. So, kind of behind that mirror is where they're looking at their image. So most telescopes are reflectors. There's too many R's. Most telescopes are reflecting telescopes. There are some advantages to those.
Are the mirrors doing like a magnification thing?
The mirrors are helping concentrate the light because they're right at the right angle to a certain point. That's what the mirrors do. Yep. An important advantage of mirrors and a reflecting telescope is that you can support them from the back. You can have like a piece of wood back here, and then your sagging glass doesn't sag anymore because it's mounted on a piece of wood. Okay, all you care about is that reflective surface on the front. Unlike the lens, you have to have it opaque. You have to have it so light can go through it. So these are twins, road trip. These are twin telescopes on Hawaii. And you can see a little person in there. Now, can you guys see the little, what are these, six-sided? Like little, yeah. Those are actually kind of segments within the mirror. And one of the last slides I have is that if you go ahead and if you have your reflecting telescope segmented like that, you can go ahead and kind of alter just a little bit the angle. And what they do is they alter the angle to compensate for the Earth's atmosphere. I know, you're like, are you serious? So basically they have another monitor to find out what the Earth's atmosphere is doing, and then they compensate for that. Are you serious? It's called adaptive optics. All right, cousins. When I say cousins, hopefully you think of the whole...
Yeah.
Yes. You think of the gamma rays and X-rays and ultraviolet and visible and infrared and what do we have? Microwaves, thank you, and radio waves. Perfect. Those are cousins. Okay? And we have telescopes to look at different cousins. Of course, this one's looking at visible light. Okay? But we have telescopes that look at short waves and long waves. The long wave, looking at okay, this is my long wave, okay? So the problem here is to get a repeating unit, to get a whole wavelength, you got to have a really big telescope to capture those, okay? So radio wave telescope dishes are very, very big. So there's this technique called interferometry. Basically what they do is they have a dish here, 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 and they take this from the same object, signals, and they combine them. They make one signal. Okay, that's interferometry. Now the short wavelengths, you don't be so big, but the problem with them is they're so darn energetic that they are hard to gather. It can be done. I think I'm going to show you how they do that. So I don't have anything for scale, but trees are pretty big, right? Okay. So this is a radio. This is catching radio wavelengths. If you've ever watched the movie Contact, which it's been a long time since I have, with Jodie Foster, right? Yeah. Radio wave, concentrating radio waves can be a good thing to learning what's out there. So what are these kind of things in the sky here? It looks like a bullseye. Circumpolar star or star trails. Very good. You can kind of see that fleet of, they look like satellite dishes, don't they? And I'm thinking the way this works is some of these, maybe not this location, but actually are on rail cars, so you can kind of move them where you want to, where they need to be. All right. So those short wavelengths are pesky. They're hard to get to. So we kind of basically have a glancing blow, slow them down, and concentrate them. Hopefully you guys would say X-rays, are they long waves or short waves? They are short, yes. Very energetic. I'm going to talk about a few telescopes that are orbiting the Earth. Okay, let me grab my Earth here. And the Chandra telescope is one of them. The Hubble Space Telescope is another one. Right. Okay, so there are telescopes, like there are satellites, that are just orbiting the Earth. This is one of them. What do you think these things on the side are? What do they look like?
Solar panels.
They look like solar panels. Yeah, they are solar panels. Okay, so why would you want to put a telescope in outer space? Well, there are several reasons. One of them is light pollution from humans or from the sun. Well, that would work. Another thing is if you have a telescope out here, then you don't need to worry about this. What's this? Atmosphere, yep. Exactly, if it's orbiting the Earth. Here, side by side, I have a couple of images. They're taken of kind of the same field of stars. This first one actually was taken with a telescope on Earth. And I don't know, I'm kind of like, get that in focus, right? But the reason they can't get it in focus is because of the Earth's atmosphere. You go out beyond the Earth's atmosphere and you can get sharp images like that. Road trip.
Can we put a telescope around the orbit of the moon so we can get like an eclipse?
Telescope orbiting the moon. Seems like I don't know about a telescope. I've heard about putting telescopes on the moon, but not orbiting the moon. I like that idea though, because then, like you said, we can see our Earth eclipse the sun. I haven't heard anything about that. Another one is, well, this isn't leaving the Earth's atmosphere, but kind of going, if you climb a mountain, the air gets thinner and thinner. Okay, so there's less of the Earth's atmosphere. So that's a possibility. I can remember, finding out about the twin tech telescopes we saw a minute ago with the little guy on it. Okay, it's like, would you really want to make them on an island? Because they're surrounded by water. But I guess they have a lot of good days for viewing them. So what this is doing, this blue right here, this kind of blue is this. That's the Earth's atmosphere. And hopefully you see the cousins across the top. We have gamma rays, X-rays, ultraviolet, visible, infrared, radio. This kind of fun. Okay? So there's the cousins at the top, starting from short to long. And kind of how long that arrow goes is how much it can get through to penetrate. So what sort of cousin do you see going all the way through Earth's atmosphere? Visible light. What sort of energy do you see is shortest? Ultraviolet's kind of what I'm seeing is shortest, yeah. So across the top then are actually telescopes that are orbiting the Earth. So we talked about the Chandra looking at gamma rays, or X-rays I guess it is. Of course everybody loves the Hubble. Yep. Spitzer is infrared, and Planck is even longer wavelength than that. We have Swift and Fermi kind of in the short wavelength. It's a busy place in outer space, orbiting the Earth, I think. Okay. So this is the last slide on here, right? So I kind of mentioned the whole segmented mirrors, remember? Where you can kind of... So if you are stuck on Earth, you can actually get a fighting chance to kind of, if it is a, I think this would only apply to reflecting telescopes, segmented, you can kind of see what your turbulence is like and then adjust your moment by moment the shape of your lens. Or excuse me, not your lens, shape of your mirror. Is that not cool or what? That kind of boggles my mind. Yeah. What's that?
Do you ever catch them when they're orbiting? Does anybody
Oh.
ever catch them orbiting when they're looking?
Actually,
Sorry, you just couldn't read it.
there is a website, and it is called Heavens, plural, heavens-above.com. It's just a website. And in order for it to work for you, this is how you see satellites.
Yeah, that's what
Yep. And in order for it to work for you, you need to tell it where you are, because that makes sense. Like if I'm over here, I'm not going to see a satellite, but I will over here. Now, when we see a satellite, I'll warn you that it's not, you don't see the satellite. You basically see, you've probably seen it before, where it doesn't look like a plane because it doesn't blink. It's just basically a light that comes, and a lot of times, and it goes about that fast across the sky, okay? And then it kind of, you can't see it. And the reason you're seeing that satellite actually has to do with it. What are these? You guys told me that on the Chandra telescope, there are solar panels. Thank you. These are my solar panels.
Okay.
Yeah, you're fine. So the solar panels actually for the satellites are what is actually getting light from the sun and sending it down to Earth so you can actually see that satellite from the solar panels. So this is great for satellites. Yes, about satellites. But it's also great for comets too.
And the comments.
And the comet. There's a link on there for comets. Yes. And that should tell us, because that's what I'm going to check for, like a map of Hercules.
Yeah,
just
to
kind of
see
show me.
what-
Yes. So that will do that too. And it doesn't need to know your location for that. But.
Okay. Thank you for sharing that. That's awesome.
So we're going to go back and pick up a few slides. We're not done for today. Any questions about all of this? Oh, before we go back, I was going to show you a few more things. What does this look like? A giant mirror. And now when I do this, put on my dew shield. Now what do you think this could do for us? It's not a mirror, it's actually just it's like welder's material. Now we can look at the sun. Yep, this is for solar viewing. So we'll definitely, yes, do this later. A few other things, just to kind of a reminder. What are these? Binoculars. And I'll take these out Wednesday because there are some awesome things just to be seen with just binoculars. What's that? Flashlight. What's it got on the end of it? It's red. Yeah. So the thing about, have you ever heard like night vision? It takes you a while to get your night vision. So one of the things about your night vision is once you have it, if you look at a bright light, if you look at white light, there goes your night vision. So red actually is the route for you. And it's a hobby for me. Like, so here's a fancy red light. Well, not really all that fancy. It's got duct tape on it. How fancy could that be? It's been dropped a few times. But you might have seen these before at Walmart. I don't know if okay, they're great.
Oh, that's cool.
You look like a geek, but what the heck?
So we're like outside trying to read the map thing
Yes.
and look at the stars, use one of those instead of a flashlight.
Yes.
Cool.
Yep. So, and then I guess the other thing I have in my backpack is this is like a bird book, but it's just all about stars and stuff. So at the observatory, everybody has their favorite. So this is kind of mine. I just kind of keep it handy if I want to kind of look at things. And then I guess I have a notebook to kind of jot down things. If I go out and I observe something, nobody else might care, but I care, and I just jot it down in my notebook. I also have the blog that I add to sometimes. Okay, so we have just a little bit. Let's see how much we can finish up. So I think I skipped this slide. Do you guys have this slide? I think that was hidden when I did. Let's find this slide. No. Yay, no.
The one that talks about it.
Nope. This is right, I moved it. Yeah, so, well, okay, so you can't find it. But, so let me describe what you're looking at. All right. I didn't kill myself last time. Okay, so, I'm going to step up. Am I absorbing energy or releasing energy? I'm absorbing it. So will I be a bright line or dark line? I'm absorbing it.
Dark?
Dark, it's dark, yep. Darkening, sucking it, yep. So here we go, right here. That's what's happening there. Dark lines. Now, see this red up here? All that red is kind of showing you is, can you see the dips in the red? That's saying that the intensity went down, and it went down, and it went down to those, whatever they are, 5 lines. 6, 7 lines. Okay, that's what the dips are. That's what this line is, just intensity. That's what the dips are. Okay, so I'm up here. I absorbed, okay, and now I'm going to step down. Do I absorb or emit light? I emit it. And that would be these guys over here. Okay? So what happened to the line there? You have spikes. Yeah. And it's characteristic of basically that jump that I took. Those are characteristic of the step that I took. Those are characteristics of the jump that I took. Okay. And then you do have this slide, though. This one of the sun. So how many people think that these are absorption lines? How many people think these are emission lines? How many people think these are absorption lines? Why are they absorption lines? Because they're black, they're dark. Basically what happens in the sun's atmosphere is there's certain material that is sucking up energy right at those wavelengths. We'll be talking more about the sun. But yep.
So there's no emission lines at all?
We could make a kind of, if you're familiar with kind of like, she asked about emission lines. What is it? Negative. You know, like if you look at a photo negative, okay? Yeah, we could have actually, we'd have to take it from a different angle, but some way we could, from the same gases that are being excited, we could get a spectra with emission lines. Yep, in the same places. Yep. Yeah. Okay. Well, you guys have some questions over this, I know, on your homework, so let's see what we can do with these. Now, one of the things you probably would know is that if you take a black poker and you put it in a fire, what happens to the end of the poker? It starts to glow, exactly. When it's out of the fire, does it glow? Nope. When it's in the fire and you take it out, it starts to glow. It heated up. So that glowing, actually, we could go ahead and we could understand that glowing and create what we call a curve from that glowing. So, there are 2 laws that I want you to know. Okay. The first law, now we could go back to our poker, or go back to our thing, okay? If you put it in there for 5 minutes and take it out, it's going to glow. If you put it in there for 10 minutes, get it hotter, is it going to glow more? That's it. That's it. That's all the first law is. As an object becomes hotter, it glows more brightly. And by glowing more brightly, actually, we're going to see that actually on an intensity scale, it's higher. This is low glow, this is high glow, okay? So, now the other one, I'm kind of excited because we talked a little about in here that, have you noticed that not all stars are the same color? What colors, what's your favorite color of star? What colors have you seen the stars be? Blue. What have you seen?
Beetlejuice is the color that I like.
It's kind of, what would you call it? Orangish, reddish?
Orange, reddish.
Yeah, blue, orangish, reddish. Maybe yellow. I haven't seen any green ones. But, yeah, those are the blue, sometimes white, okay? And so the color of the star actually kind of gives us an indication of what its surface temperature is, not the temperature in the center of the star, but what the temperature on the outside of the star is. And here, okay, this works for you maybe. I'm going to go over here, I think. And if we want to do the colors of the rainbow, what name do we do? What is it? It's
Red, orange, yellow, green, blue.
very good. You got it. Bumping up against red, we have infrared, and bumping up against violet, we have what? Ultraviolet, exactly. So this is short wavelength, this is long wavelength. And as it turns out, do you buy this? That actually, and this is what this says, with regard to a cooler object, you're going to actually see it, if it's cooler, you're going to see it at this longer wavelength. So this is going to be cool, this is going to be hot. See? It's kind of consistent with what we've been talking about. Good. So now you know, when you look at that, which one's hotter, the blue or the red? The blue, exactly. The blue is hotter. Sometimes I'll run into students, and I don't want to throw you off, but they'll be like, well, I remember red hot, but you know, it's blue is hot, and red is cooler. Exactly. So we end up with these kind of things, these kind of pictures. Remember when I said this is high intensity, this is low intensity? Okay, that's what these curves are all about. Along the, I guess we call it the y-axis, we have intensity. Along the x-axis, we have the cousins, okay, the different wavelengths. You kind of see the Roy G. Biv going backward, visible. So we can kind of see both of these things going on. I've got, let's see, 1, 2, 3, 4 curves up there. These are called thermal radiation curves. Which one do you think is the hottest? This purple one, or this red one? How many people think the purple is the hottest? Cool, awesome. It's actually hot in two ways. Can you see where it goes up higher? And it's this way. I love it. Okay? And actually, these are actually fingerprints of stars at different surface temperatures. We talked about the Kelvin temperature scale, so this star has a very hot surface temperature. Our sun's about 5,800 Kelvin. And then one of my favorite, you see that little brown thing down there? Is that not a black thing down there? Not brown. It's us. We would make a little radiation curve like this. Okay. Do we glow visible light? No, but do we glow thermal energy? Yeah. Oh, that is so cool. Okay. Well, I think that's about, you're gonna, we're close. We'll finish these up on Monday, these slides. But if you have any questions about the Doppler effect, just do your best on your chapter 5.